Good morning and welcome to the O-Scope Wizard. In the chat we were talking about trips we've taken. Trips are becoming super rare and kind of weird and unusual, but we're getting out there into the world and hopefully everybody is staying safe. Had a wonderful weekend. It is Tuesday. No show last Thursday, kind of threw a lot of people for a loop, but as I said, I was on a trip, which is exciting and new for me. I mean, I've done many trips. It's just I haven't done trips in quite a while. But we are back in the techno lair today. I am Gabe, the O-Scope Wizard. Thank you so much for joining me. We are still on our quest to build a DIY Sonos style amplifier, and I am running into all sorts of exciting learning opportunities, I would say. Over the weekend, I got a new digital potentiometer. Digital potentiometers are becoming my white whale. I feel like Ahab chasing the white whale of Moby Dick, and they are sinking my boat. Over and over again, I am failing at first, failing at choosing the right potentiometer. And then once I do get the right potentiometer, I tried 3 times. I got this new potentiometer. It was a 2-channel audio potentiometer. And I tried soldering it on here. Let's see if we can see my work. Let's see. See if you can find it, camera. Find it. Maybe it can't find it. You'll just have to see a blur and trust me about it. I tried once soldering. Give up. So I tried a second time, soldering, killed the part. I thought, you know what? I have 3 parts and 3 boards, so let's try a third time. Guys, I am terrible at soldering. My soldering iron is worn out. The tip is worn out, so it doesn't melt the solder properly. I've ordered some new soldering tips, so hopefully that will help transfer the heat more effectively without having to use quite as much heat to melt the solder. My soldering iron to overcome the junk on the edge of the soldering iron tip. I was cranking the heat up, which is fine when you're dealing with like header pins, when I'm trying to just solder headers into a board or passive resistors, but when you're messing with delicate digital potentiometers, apparently they don't want to be baked at 1,000,000 degrees in order to stick the legs down. So that aside, that's actually not what we're going to do today. I'm going to continue trying to hunt that white whale on my own with some better soldering equipment, and hopefully I got a different package that has a slightly larger lead spacing. I don't know. I'm learning a lot going along, trying to make all this happen. The chat is asking, did I try a hot air solution? No. I wish I had a hot air soldering iron or a hot air soldering station. I just have a Weller soldering iron that I got a couple of years ago for car audio cables, and I've been using it for all sorts of things, and the tip's worn out. But you're right. When I did soldering in a lab professionally, I guess I'm sort of doing soldering in a lab. As I talk through this, I realize my mistake. But when I worked in a lab with a hot air station, I used that to put down the surface mount parts, and it worked a charm. Using a big old huge soldering irons, a little tougher for me. Oh man, somebody in the chat saying they have a microscope soldering station, and they might be able to put the board. You know what? I'll take you up on that offer if I can't get the next one down. I've got like 5 more tries. I ordered 5 more parts to see if I can get this done, in hopes that I could solder. But I keep soldering it down, and it won't talk with I2C. Well, let's get to the meat of the show, though. What are we doing today? Today, we are actually going to look at DC to DC converters. Let's turn on my let's type it in actually. What are we doing today? Today we're looking at cheap cheap being the key, cheap DC to DC converters. Very cheap. That's the trick. We are looking at cheap DC to DC converters. I'm talking about converters that cost less than $5. We've been using the same converters for quite a while. So I bought these converters when I began the quest to build my DIY Sonos style amplifier, because I needed a 5-volt rail and I needed a 3.3 volt rail. And I thought, you know, the Raspberry Pi itself in the GPIO pins, if I point it over here, has a 5-volt rail and a 3.3 volt rail coming off of the GPIO header. But those are super noisy, and I drastically underestimated the effect that that noise would have on my setup. So I have, you know, about faced, I guess, thought about it, trying to make it a little bit better. So I realized that I couldn't run the Raspberry Pi off the same power supply that my audio equipment is. So my little digital to analog converter chip over here, this has to have a separate supply. So that forced me to have at least 2 DC to DC converters. So I have one for 3.3 and one for 5 volts over here. But something strange is happening. These guys are pretty noisy on their own. But as I sat by this amplifier and just listened to it with nothing playing, I could begin to hear, like if I put my ear down to it, you can see you can hear something on these boards making noise. And I think it's probably the inductor that they're using on this board. I mean, they're using the cheapest components ever because they're sub $5. So I bought more DC to DC converters, because why not? So I bought another one off of Amazon, and then I have a third DC to DC converter. All of these guys are slightly different. They use different chips. They have different layouts. They are rated for different power levels, and we are going to compare today the noise coming out of this guy, our original DC to DC converter, the noise coming out of this one, our mid-size DC to DC converter. Let's scooch it over so you can see it good. And then we're going to compare it to this tiny itty bitty DC to DC converter. So let's look at the first one really quickly. This is what I initially purchased. I was excited because it has a 7-segment display on it, and it reads the voltage out. So it's really easy to set up a 5-volt rail or a 3.3 volt rail because of these LEDs. It makes it super easy. But this thing is kind of gigantic when it comes down to it. So having all these extra components on here to both read the voltage and then display the voltage makes the whole board so like relatively large. But it uses an LM2596 part, and you can see it costs $4. So I have a notepad over here that I'm going to keep track of some stats. Oh, you know what? Before I get too far down the road of keeping track of stats, let's set up my timer to keep me somewhat on time. 20 minutes. Here we go. Let's see how far we can get. The chat's saying they can't believe people are building power supplies for $5. It is kind of amazing. But I have this original one, the LM2596. It cost $3.96 now, so it's super cheap. When I bought it, it was actually $2.96, so it's gone up $1. The inflation on this particular DC to DC converter is out of control. If inflation worked that way in real life, whew, it'd be tough to keep up with. So that one was $3. That one is $3.96 now. And then I bought this mid one. This what is a 4-pack for $12.99. So $12.99 divided by 4. Some quick math in here. We got any quick math whizzes? 13 divided by 4. Calculator. There we go. Calendar. Did I do calendar? Calculator. Calculator. Read the words. All right. We have gotten it into programmer's language, but we don't need 13 divided by 4. $3.25. So this mid-sized one is $3.25. Probably should have been able to work that out in my head. It's a little harder to do in front of people. This is updated from the LM2596. So the original one that I had was an LM2596. This guy is a XL405E. So XL405E. If I go back over here, so the XL405E was $3.25. This is probably the most important metric that we are going to measure today. What was the cost of this DC to DC converter? There's always a cost benefit analysis when you're doing engineering, but $3.25 for this guy. It is much smaller. It has a machine, probably a machine wound inductor, but a big old wound inductor, which I hope would be quieter, audibly quieter. And then finally, I have the tiny, itty bitty MP 1584EN DC to DC converter, $9.55 for a 6-pack. That's cheap. $9.55 for a 6-pack. Why did I close my calculator? I don't know. $9.55 divided by 6. Free shipping. How is anybody making money? I'm talking about this thing costs $1.59. $1.59. All right, so that is the cheapest DC to DC converter. It's also the smallest, which is kind of cool. So this is the MP 1584. I'm honestly, guys, I'm pulling for this one because it's so tiny. Like, look how much smaller it is to the original DC to DC converter that I bought. Let's get a better shot, a better angle, just straight down. Look at that. I mean, one is tiny. It's teeny tiny compared to this guy. And it costs $1.59. And allegedly can give me power. So my question is, what am I sacrificing? I want to compare the noise at 5 volts, the noise at 3.3 volts. I want to maybe do a low-pass filter and see what it looks like. Oh, man. There's some shade being thrown in the chat saying when you steal someone else's design, it's really easy to make cheap parts. That is a fair point. But my goodness. I mean, I don't even know how you're putting this together for $1.59. I couldn't build that for $1.59. That's out of control. And then finally, I have a battery pack. So this will be the gold standard of quiet noise rails. I think we'll test it. But I have 4 rechargeable batteries. Each of them are 1.2 volts. So 4 times 1.2 should be 4.8 or about 5 volts. So that'll kind of give us an idea of what I could expect when I compare my DC to DC converter to my true DC source based on a chemical reaction. And we are using these DC to DC converters to convert my 24-volt system, my 24-volt power supply, my big old huge power supply over here, this big old giant thing, down to 5 volts or 3.3 volts. And I have, to help me today, my handy dandy power rail probe, the ZPR20. I like it because it has a big offset and I can zoom way in and look at the tiniest little noise. So we're just gonna, I mean, honestly, disconnect everything from the power supply except for the input voltage and then measure the noise on the power rail. So I have my handy dandy header adapter on my power rail probe. That should make it easier, but everything's a little bit more difficult when you're doing it in front of people. Measure it with a load. That is a good point. Let's measure it loaded and unloaded. I think I can make that happen. I'll tell you what, if you measure it loaded on the Raspberry Pi, it is a hot mess. Because the Raspberry Pi just makes so much noise. Soldering on camera is fun. People enjoy it. But I branded myself. My thumb is branded from soldering the other day and grabbing something hot. It's a mess. Okay, so set to 5 volts. Preset my scope. Now let's open up my probe meter. So the probe meter is going to tell me where the voltage is. Cool. My voltage is at 5 volts. And there is the power rail right there. Boom. Let's make it a little bit more sensitive. And let's do a little bit more time. So I'm looking at hardly any time. We need more time. More time. Instead of 100 nanoseconds. That is the wrong direction. Let's get a millisecond. Let's see. A good rule of thumb is 1% of the switching converter's max output load to load it down. Well, the Raspberry Pi will definitely have more than 1%, and we can see what it looks like with load. So let's compare it loaded and unloaded and at different voltage levels. These are all good points. It's a good thing I have some help out here. I don't know what would happen if I didn't have help. I'd be operating in a vacuum. Okay, so 20 millivolts per division looks like we're fitting. Here is my power rail. Now I am sampling this at 200 megasamples a second. I'm allowing 2 gigahertz of bandwidth in here. I don't want to do that. I do want to limit the bandwidth that I'm looking at down to megahertz. Because again, I am most concerned with fairly low frequency components. Although at a megahertz, I think the switching frequency of almost all of these power DC to DC converters are below a megahertz. So we should see the switching frequency. But all right, making some measurements. First measurement, amplitude measurement on channel 1. I probably needed statistics. We're going to write stuff down, folks. I have a pen and paper here to write it down. So this is 5 volts unloaded, 5 volts unloaded. So we'll do 5 volts unloaded, and then we'll do 5 volts loaded. 5 volts unloaded is 35 millivolts of noise. So I'm looking at this here for my amplitude of my signal here. 35 millivolts of noise. Out of curiosity, I'm going to do a second measurement of peak to peak. I think I'm more concerned about peak to peak than I am of amplitude. So well, now I have 2 measurement groups on. Holy moly. Who is running this show? Let's turn off measurement group 2. I don't want you on. Holy moly. All right, we're good. Okay, peak to peak, 48 millivolts is the worst case. This is unloaded. So I'm going to write on my paper here, we'll say unloaded. And then I will make a second column for loaded. And unloaded was 48 millivolts. 48 millivolts. For the LM2596. Now, if I load it, I load it up, how am I going to measure it? I have a way. I have a way. I have some little clips over here that'll allow me to clip on. So let's see if we can clip on to our wires. Because I'm thinking down the road we're going to have to do this on all of them. I want to make this as easy as possible with as low a likelihood of a shock as possible. We're always trying to minimize the likelihoods of shocks. Okay? Okay. Let's reset that. Okay, that is a bummer because the longer leads made more noise, and it didn't make more noise, it allowed me to see more noise. And that is one of the struggles that I will have trying to get onto. What if we accepted more noise and understood what we are going to try to accomplish with loaded versus unloaded? I think if we do everything the same, the numbers may be inflated, but they will all relatively be at the same level. So that's what we're going to do. So instead of 48 millivolts, we will write down 75 millivolts. Another option I have is lowering the frequency. It's just important that once we start making the measurements, that all the measurements remain the same. Okay, I'm going to lower this down to, let's say let's see if 500 kilohertz will, 500 megahertz, dude. 500 kilohertz. What does that do for me? I like that. I feel good about 500 kilohertz. Still well above the audio range. But I'm trying to filter off some of the things that I'm catching from adding extra probes. So, okay. We are going to write down 51 millivolts for unloaded. And now we will load it. Now this is where it will get exciting because it will be well good and loaded. Oh, I need to change the camera so that you can see me making the connections so that I can embarrass myself fully as I try to connect things. Well, that is ground. Ooh. All right, speakers. All right, speakers. That is loaded. Holy moly. This is loaded. So it went from 51 millivolts to not 51 millivolts anymore. And this is, honestly, guys, the Raspberry Pi. Just so noisy. It's unbelievably noisy. Look at this. 400 millivolts. 400 millivolts. This is a 5-volt rail. 400 millivolts. It's just, I feel like I need a different load, an easier load. Huh. Yeah. I don't know. If you have an idea for a good load, I had not thought about a spectacular load, and so now I have this really bad, super noisy load, but it's, 450 millivolts max now loaded with the Raspberry Pi. What if I loaded it, instead of with the Raspberry Pi, I loaded it with the DAC, the quieter section, because it would still be a load. It would be a quieter load. Let's just compare it. So I'm going to do some tooling around here real quick. Let's unplug what I have, because I have kind of a mess on my hands. We're going to continue measuring the same thing. I'm going to unplug the Raspberry Pi because it's a hot mess. Let's unplug my DAC section from over here. be okay. This is the quiet side of the board that I'm working on, or what I call the quiet side. And I'm going to unplug that and that. Okay, and I have a longer wire. Just refuse to accept 400 millivolts of noise on a 5-volt rail is ridiculous. What is that? That's almost 10% noise. 10% noise? What in the world? That is basically like your kids screaming in the background while you're trying to have a very serious conversation about mathematical concepts. Or yesterday, I rolled into a meeting thinking we were going to talk about one thing, and I suddenly had a pretty detailed explanation of quantum mechanics. Sometimes you can be surprised. Okay. Whew. Okay, that is much better. That just shows you how noisy the Raspberry Pi is. Look at that, guys. Look at that. That's crazy. Okay, so now we're loaded. So we went from loaded to unloaded. All right. We went from unloaded to loaded. This thing on the screen. Look at that. We're doing great. This is good news. It's actually quieter loaded. So that's probably good. So loaded, it went from 51 millivolts down to 44 millivolts. That's good. So that was the LM2596. Now, that was at 5 volts. Oh my goodness, and I didn't show you. Let's show you. Oh, somebody said one of my concrete resistors. I thought about that. I've made enough burn marks on my desk using those concrete resistors, and these guys are capable of up to 5 amps. So it would be 5 amps through 8 ohms. It would be hot. It would be hot, I think. I didn't want to burn my fingers anymore, but I did think about that, the concrete resistor. That's probably, I don't know if that's a better option or not, but this is working well. 45 millivolts. So that was 5 volts. I need to change this from 5 volts down to 3 volts. I'm going to use my screwdriver here to reduce the voltage, and you'll see, whoop, drops off the screen. I have a screwdriver there. You can see I'm just adjusting the potentiometer, but I have the probe meter showing me when I get to 3.3 volts. So, holy moly, only one. We got
5 minutes remaining.
Now that we have our measurement methodology, though, we'll be okay. We'll be okay. We can stick with it. All right, 3.3 volts. All right, probe meters, 3.3 volts. Push the button that copy to offset was always active. That would be awesome. Oh, a little more noise at 3.3 volts. A little more noise. Ooh, you can see occasionally it gets a spike up there at 108 millivolts. So that is loaded at 3.3. Loaded. 3.3, we will write down 111 millivolts. And then unloaded, so we will disconnect my load. What are we measuring here? Unloaded, reset it, 59 millivolts. So it was 51 millivolts at 5 volts, 59 millivolts here at 3.3 volts, and feels pretty good. That was us measuring some DC to DC converters. Let's measure one more DC to DC converter, and then maybe we'll measure the third one on Thursday, or maybe we'll have enough time to measure it today. I'm going to now disconnect some stuff from my 24 volt side of my DC to DC converter, because I'm going to use these wires over here power these little guys. We'll start with this one. This is my XL40 0.15. I want the little one to win. I think this one's gonna win. I feel like that inductor feels like a $2 inductor. That what did that cost? That cost $3. This cost $3.25. Two of those dollars are that inductor. I think it's gonna be great. Gonna be great. Let's set it up so that I can hit my load easily, right? My favorite stuff, my tacky silly putty. Stick it on here. And then I have some cables, some wires to make positive and negative connection. And we'll see if we can do all of this without even shocking myself one time. I've managed to not shock myself badly in quite a while. 24 volts probably won't shock me. I also don't want to break my stuff. Okay, so we will plug this in, make my connection for my oscilloscope. Okay, there we are. Now we're looking at the output of my XL405 DC to DC converter. Not sure what the voltage is set at. Oh, looks like from my oscilloscope that the voltage is set at 5 volts. So we'll start there. We'll start making our measurements there. Real quick, copy to offset. This is unloaded. So unloaded at 5 volts is 30 millivolts. So that's already quite a bit quieter than the first one. So 30 millivolts. And now let's load it real quick without shocking myself or anyone else. Loaded. Reset it. 35 millivolts loaded at 5 volts. That's really quiet. That is much quieter than the other one because I was at 51 and 44, so 10 millivolts quieter, which in the grand scheme of things is probably not that much quieter, but it's also much smaller. Much smaller. Let's change down to 3.3 volts. Oh my goodness. Oh my goodness. the potentiometer here has got so many turns to make a change. Where are we at? 3.3 volts. Almost exactly 3.3 volts according to my probe meter. Let's copy to offset. There we go. We are still loaded. So this is my loaded measurement at 3.3 volts. Where are we at? Yeah, 35 millivolts. Looking like a champ. So its noise remained the same. If you remember, the LM2596, when it was loaded, went up to 111 millivolts, which is more millivolts. So then we'll do unloaded. Unloaded. Oh, don't fall off, please. Don't fall off. Almost fell off. Now unloaded, 28 millivolts. So 28. Everybody following along still, hopefully. This is very exciting, very exciting. Now, I am going to try the last little one, the tiny guy. The MP 1584, purchased for a grand total of $1.59. And then, it will be time for lunch for me. I'm excited about lunch today. Every day, pretty much. Lately, I have been making myself an Asian soup. I think today it is going to be spicy tofu. Let's make sure I plug this in right. The words, for $1.59, you don't get a lot of words on the top. And also, look at the tiny potentiometer. This little potentiometer is itty bitty. Okay, so in negative, let's plug in negative, so I don't plug it in backwards. And in positive, like input. Like in is also stands for negative a lot, but I mean input. Input positive. Okay. Okay. That feels pretty good. Let's plug in the oscilloscope probe. Now, mind you, I am using a low pass filter of 500 kilohertz because that's really kind of the world that I am concerned about. Super low frequency audio level stuff. In real life, people may be concerned about voltages that are frequencies that are higher, but it looks like it is set already, ready to go, 5 volts. So let's, and once again, I probably should just leave it out, right? Copy off, leave it out. This one is pretty quiet, but it has a weird shape, doesn't it? So 5 volts unloaded for the $1.59 DC to DC converter is 64 millivolts. It's actually losing the unloaded. No, I wanted it to win because it's so tiny. Ah, bummer. It's got a real rhythmic. I want to say rhythmic. Periodic. That's what I'm looking. The word I'm looking for is not rhythmic. It is periodic. Copy to offset is also one of my favorite buttons. Chat was saying it was one of their favorite buttons. I agree. Okay. Yeah. Okay. So 64. Let's not cry over spilled milk. Now let's test this thing loaded. So we will load it back up with our device. So plug negative into negative and positive into positive. No, it's pretty loud. The noise now is, well, 69 millivolts instead of 67. I'll write it down. 2 millivolts more because I waited so long to write. I got to write quicker to save this little guy's dignity. Let's lower it down to 3.3 volts and see how it operates at 3.3 volts with the tiniest screwdrivers ever. Teeny tiny little screwdriver that I will use to lower the voltage. I think. Come on, 3.3 volts, 3.2, 3.3. I'll have to breathe through that. Copy to offset. Copy to offset. There we are. 3.3 volts. This is loaded at 3.3 volts. Oh, it's much quieter at 3.3 volts, which is good. So loaded 3.3 volts, 40 millivolts. Huh. That's in the ballpark. 41 millivolts. Don't look at it too long. Don't look at it too long. And then unloaded at 3.3 volts. Pull off my load. Unloaded at 3.3 volts. We have this, you can see where it goes down to this triangle shape. Looks like it's 53. So it really wants to be loaded. Unloaded, it is not happy. It is not a happy camper unloaded. So 53 millivolts unloaded. I'm just curious, like what is the frequency of this thing? I just do a bog standard frequency measurement. Find it. Frequency of channel 1. Why do you keep making new measurement groups? Why do you keep making new measurement groups? I wanted I wanted a frequency measurement here. Stop making new measurement groups. 180 kilohertz. 180 kilohertz. That makes sense because when I looked at the data sheet, it said it would switch down to 180 kilohertz to save power, but then when it was actually loaded, it goes up to 1.5 kilohertz. So that makes sense. That makes sense. In fact, if I reload it real quick, just to see how the frequency changes, make sure not to plug my stuff in backwards. So there's loaded. Now it's just having trouble. Now it's just having trouble finding it. There we go. Trigger on it. What are we looking like? Struggling to find it. Struggling. What's the frequency? I drop down. If the frequency actually, man, 50 kilohertz? I don't know. It's just struggling. That measurement is struggling. I'd have to probably set up a marker. Single. Let's do a cursor real quick. Cursor. Enable. All right, from here, here. What's the frequency? Oh, 9.6 kilohertz. That is a low frequency thing. Odd. And then unloaded. Unloaded. I don't know why I'm spending so much time on this little one. It's just I was pulling for it, guys. I was pulling for it. I wanted it to be awesome. Where did my markers go? Enable them again. What is the frequency here? Because this is crazy. 1.1 kilohertz. 1.6 kilohertz. Okay. 1.6 kilohertz would not be a spectacular frequency to have hooked up to an audio system because you can hear 1.6 kilohertz quite well. It is in the frequency range of most people's ear holes. And then last measurement of the day, I promise. Last measurement. Let's measure the battery pack. What does a battery pack? How does it roll? How does it? I mean, it's going to be 5 volts because I don't have. I could change the number of batteries and make a 3 volt, but let's just measure the battery pack, loaded and unloaded, and see what noise it's going to have as sort of like the golden standard, quietest possible measurements that we can make. Yeah, even old guys can hear 1.6 kilohertz. That is so true. Anybody, pretty much, if you got ear holes and they work, you can hear 1.6 kilohertz. All right, so the battery pack is hooked up, unloaded to my scope probe. Let us return. Where did my probe meter go? Why? Why are you doing this to me? Open my probe meter back up. I don't know what. Am I clicking stuff wrong, guys? Am I clicking stuff wrong and I'm not noticing it? Oh, let's turn on the battery pack and let's do that. Boom, there we go. That makes a lot more sense. 5.1 volts. Copy to offset. Look at the noise on this. Holy moly. So, oh my gosh. Batteries are so quiet. They're so quiet. Everything else was like 30 millivolts, 60 millivolts, 80 millivolts, 130 microvolts. Batteries win the day. I mean, one option, I thought about this while I was getting ready this morning super early, jumping around outside, get my mind right. Look at 109 microvolts compared to, what was our best one? 28 millivolts? What I thought about was, what if I hooked the whole thing up, except for, let's come to me, come to me, and let's just talk about this. I thought about, what if we hooked the whole thing up? You know, before I do that, go back and let's load it. All right, we'll load it and just look at it loaded. What does a battery look like loaded? 130 microvolts. All right, so now we're loaded. You can immediately see, load. Wait, it's not 130 microvolts anymore, but this is all the load causing this noise. We're still, I mean, still crushing everything else, right? Look at this. 17 millivolts. 17 millivolts. Less than half of the noise of anything else loaded. Unbelievable. Batteries are so quiet. So what I thought was, what if I designed the whole circuit to be run off of batteries, rechargeable batteries like this, and then designed a charging circuit that turned on to cap these batteries up when the audio was off, and when the audio was on, what if you just ran off of batteries? It would be so quiet. It would be essentially as quiet as, like, by quiet I mean the power supply noise would be as quiet as possible. That was one thought I had, which would be crazy. Thomas is saying, hey, what about linear regulators in the chat? That is another possibility that I thought of. So I could use these cheap $1.59 this tiny regulator right here, the teeny tiny guy. Can you zoom in? Can we find it? There we go. This teeny tiny guy right here for $1.59. Or the slightly larger one for $3.25. I mean, this one is pretty small, but this one is teeny tiny. This was the quietest one. This won the day. The one in my system, when it was loaded at 3.3 volts, was the, let's get it so it focuses on me again, find me. All right, the results. I should probably show the results really quickly. Let's go back. The results are, if I can make my computer work, the results are this. The original one, the LM2596 at 3.3 volts had the worst performance, but at 5 volts had second best, but it's kind of big. So I think it's out. It's definitely out. The tiny guy for $1.59 loaded was second best, 41 millivolts, definitely performed better loaded than unloaded. But then at 5 volts, it was 69 millivolts of noise, which was the worst. The worst. I mean, it is $1.59. And then the XL405, the one with the fancy, larger inductor, loaded at 3.3 volts, 35 millivolts, the quietest, and 5 volts, 35 millivolts loaded. It is XL405. I'm not even reading that. XL4015, the best one. The best one of the ones that I have. But then there was another, the linear regulator, the 7805. I wonder if I can find an inexpensive 7805 linear regulator, or if I would even see benefit of that on my audio signal, because already by having the Raspberry Pi not on the digital to analog converter, I don't hear a lot of hiss. It's pretty quiet. So I think the compromise of using this one right here, this feels like the best contender of the ones that I have. It is fairly small. It has the nice, huge, giant inductor, and it costs $3.25. So that's not bad for $3.25. Come back, and we will do more on this amplifier. This was a lot of measurements, but when you're trying to decide on what is the best component, I don't know a better way than like measuring that component and seeing how it stacks up to its competitors. Because I know I was pulling for this tiny one, and it was not very good. So there you go. It's a good thing I didn't put 6 of those in my amplifier. I should probably use this larger one, or even, I mean, I'm still thinking about that linear regulator. I hadn't even considered that. It's one of the things that I'm doing is learning on this journey, and I really appreciate you taking the time to learn with me. And I don't know all the nerds in the world, so please share this with the nerd in your life, and come back on Baby Friday. I forgot this was Band Shirt Tuesday, and I mean, I was wearing a 21 Pilot shirt the whole time, and I forgot to mention it was Band Shirt Tuesday. Hopefully you were wearing your band shirt. Tell me what band shirt you were wearing. Let me know what linear regulator board I should try. I would love to try one. Hopefully they're not gigantic. Hopefully they're pretty small, but I have a feeling they are going to be on the gigantic end of small. I will see you on Baby Friday. I'm going to hang out in the chat, and I will talk to you guys later. Bye.